pipeline using Spark, SQL, Tachyon, and Parquet. So for those of you who participated to Andrei's training, Spark training, you already have seen this slide, but I still have to mention the fact that we, both of us, we are software engineers at Tachyon. Tachyon is providing big data analytics and machine learning solutions. Tachyon has been working with Radu for more than 6 years and then switched to Spark. And this is how we end up working with Spark for the past 2 years. Besides our job, in our free time, we are involved in this big data research group that aims to provide open source solutions for technical problems that exist in the big data industry. So what we are going to speak is, we'll provide tips and tricks about how to build a in-memory data pipeline with Spark. We will speak about 2 open source projects that we are main committers on, projects that we contribute to the Spark ecosystem. I'm talking about Spark Job REST service and Spark SQL REST service codenamed JAWS. There will be a few words about Parquet file system format, and also I will go through the benefits of using Tachyon. Our use case is to build a in-memory data pipeline that will process lots of financial transactions that will be used downstream by the data scientists in order to detect fraud, for example. So the first step we will have to do is to ingest the data, to bring it from an external source like S3 into our Tachyon cluster that is backed up by HDFS. After ingesting the data, we will have to transform it in order to be able to query it and analyze it. To do this, we will have to build a data warehouse to allow us to run interactive queries on top of our data. So for the next few minutes, I will let Radu go through the first steps in this pipeline, and then I will come back for the data warehouse.
Hi, my name is Radu. I'm going to present you the first part of the pipeline, which consists in 2 steps: downloading and transforming a large amount of data. So as a distributed framework for processing, I've chosen Apache Spark. Just a few words about it. Spark is a fast and general engine for large-scale data processing. It was built around the concept of RDD, which is an immutable collection of elements partitioned across the cluster's nodes. It has a rich API consisting in 80 high-level operators, and also powers a stack of high-level tools, including Spark SQL and MLD. So for our use case, we want to download the data from an external source, a public S3 bucket named public financial transactions. Even if we are downloading from S3, the tips and tricks that I will present you apply to other external sources, so they are not bound into S3. As you can see, the structure for this bucket is very simple. The scheme file is in the scheme folder. The data files are in CSV format and are divided into multiple folders. The easiest way to download the data would be to use the method whole-text-file that Spark Context offers. As input for this method, we have a simple regular expression that consists in 2 wildcards. The first wildcard matches the folders inside the bucket, and the second wildcard matches all the files inside the folders. In order to transform from wildcards into file names, what Spark does behind the scenes is that it lists all the files metadata. And the problem with this is that listing the metadata for a large number of files that are in an external source can take a very long time. We can improve this by listing the metadata distributed. So instead of listing all the files here on the driver, basically with one single core, what we can do is list only the folders. Then we can parallelize this list, so the data is distributed to the Spark workers, and then we can list the files inside each folder in a distributed way with multiple cores on multiple machines. Okay, so now let's see the code for this. As you can see in the first part here, we're getting the folder list using an S3 client. It's not very complicated. And then we are parallelizing this list. I have to mention that it's worth parallelizing only if the number of folders is greater than 1, because when you have only one folder, then you're just moving the computation from the driver to one of the workers. So there's no delay. Okay, and after parallelizing the folder list, we can do a map or a flat map in order to list the files inside the folders. By default, the parallelize method here creates a number of partitions that depends on your cluster manager. However, in order to fine-tune this, you can specify this number of partitions by adding an extra parameter to the method call. As a tip, you should have the number of partitions as least as the available cores in your cluster in order to take advantage of your computation power. More than this, they say that the number would be 2 to 4 times the number of available cores. That should be your number of partitions. Okay, now let's move on to the download part. This is pretty easy. We're doing a map over the files RDD, so basically we're iterating on each file and initializing an S3 client and then downloading the file. The problem that might arise here is when we have unbalanced partitions. So we might end up in a situation similar to this, where the data is not even distributed among partitions. So this happens because the default partitioner is a hash partitioner, and as you might know, the hash partitioner for string types doesn't always provide an even distribution. More than that, the data inside each partition is processed by different tasks. So all the data from here will be processed by a task, and all the data from here will be provided by other tasks. So the real problem with unbalanced partition is that while some of the tasks will finish very quickly because they have less data, the rest of the tasks will struggle to finish. This will lead to an increased overall time for your stage. As a solution, we can rebalance our partitions by hashing on an integer key. So basically, we have to transform our RDD into a tuple RDD, in which to have a unique index as a key and our file name as the value. On top of this unique index, the hash partitioner would provide a fairly even distribution. Okay.
Does that mean that there is no work stealing of any kind?
Sorry?
There is no work stealing? Like, okay, I'm done with my work, I'm available to take something else?
No, you can't do that. So you have to process all the data from a partition. So it's very important how you partition the data.
So you're forced to know in advance in order to get even out.
Okay, now let's see the code for this. We can add that unique index by using the zquit index operator. This adds that index to each value from our RDD. So as you can see, we will end up with an RDD that will have our file name and our index. Okay? Then we're using the map operator in order to interchange those values so that the index ends up being the pairs key. After that, we can do a repartition with the desired number of partitions in order to shuffle the data around and to rebalance the partitions. As a warning, please keep in mind that repartitioning your data is a fairly expensive operation. However, in some use cases, the benefit of using it is greater than the penalty it inflicts. Okay, now let's move on to the data transformation. Data cleaning is the first step in any data science project. And for our use case, we have to remove the lines that don't match the structure, some of the columns that are not needed for our analysis, and we have to transform some of the columns in order to be in a consistent form. We have two columns in our use case, both representing country codes. The problem is that they are not in the same format. So one is in numeric format and one is in alphanumeric format. So in order to achieve consistency and have them in the same format, we can do a join. So we can join the transactions RDD with the RDD containing the countries, the country codes. Okay. However, the problem with joins arises when you have a key in your key distribution. So all the values for one single key have to be processed in the same task. So if one of the keys is much more frequent than the others, the task that will process that key will take much more longer to finish. Okay? So we can spot this kind of skew key distributions by looking at the metrics when running an action on top of the join transformation. So as you can see here, while 75% of the task finished in under 2 seconds, the maximum task took 17 seconds. Also, another field you might want to look into is the shuffle read field. And when you can see this kind of differences and you're doing a group by or join, it's very probable that you have a skewed key distribution. Now I'm going to present you another way of achieving this transformation. We can do this by shipping the countries, the country map, the country codes map, to the workers. So we can do that with the broadcast operator. This method is very good when the data you are shipping to the cluster is not that big, because it infers serious I/O penalties. So as you can see here in the code, after we've broadcast our country's map, we can then use it in our flat map operator. So it's very simple to achieve our transformation with a flat map. And this also adds the benefit of not having to process all the values for a key in a single task. Now we can process, we don't have keys anymore, and we can process our data in an even distribution, we say it like that. So the next slide with the picture of our metrics from running an action on top of this transformation shows us that the running times for our task now are very close in range. So you can see that now the maximum task took 8 seconds. Also, you can look at the input and see that we can say the same about it. Now I want to show you a chart with the running times for both the presented version of transformation. And as you can see, the broadcasted map version here, it's much more quicker and also looks linear, in contrast to the join transformation that looks exponential. However, this only applies when we have a skewed key distribution. Okay, now that we've implemented a downloading job and a transformation job, we have to run them. So we can run them on top of Spark Job REST, which is a RESTful server that provides context management and job submission for Spark jobs. This is an open source project, and it was created in order to solve the inability of having multiple Spark contexts in the same JVM. This is a bug in the Spark core, which also affects Uyala's Spark Job server, and from which, by the way, we started, but we faced the urge of having multiple contexts, so we came up with the solution of spinning a new process for each context we create. The inter-process communication is done with the AKA framework, and it's very lightweight. Next, I'm going to present you a short demo of Spark Job REST. Okay, so the Spark Job REST UI consists in 3 tabs: context, jobs, and jars. As you can see, here is the context tab. We can see the contexts that are running on our cluster. So I have a sample job context that is running. You can see the Spark UI port here. This is very nice because we are managing the Spark UI ports in order to provide you a quick link to the Spark UI, so you don't have to look through the logs in order to find the UI port. So you can go into the Spark UI and see what stages were run on top of your context. Okay. in order to create a context, you have to provide a jar. So the people that were in the training today saw that in order to run something on Spark, you have to provide a shaded jar. So here in the jars part, you can upload your jar. I've already uploaded the S3 download job jar, which I'm going to run. So let's create a context. Let's say download context. We have to select the jar. And now we have to specify the parameters we want for the Spark context. So here basically you can specify any Spark parameter like Spark executor memory or Spark cores number or anything you like. I'm going to set the Spark executor memory in order to tell Spark to give 4 gigabytes of RAM to each executor. Okay, when you push that context button, when the server receives the request, it spins a new process in which it initializes a Spark context. Okay, you can see that the Spark context was created, and now we can go and run a job on top of it. You have to specify the full class name for the class you want to run. So mine is com job s3 job. You have to select your context, and here you can add any parameter that you want in order to configure your job. So my job needs 3 parameters. The first is the S3 bucket we want to clone. The second one is the number of partitions in which we want to parallelize the job. And the third one is the output where I want to save the data. So I didn't specify anything about this until now, but as the title said, we want to make an in-memory data pipeline. So I want to save the data in memory, so I will write it to Tachyon. Tachyon is an in-memory file system about which Emma will talk more later. So I have to provide a valid path for Tachyon. This is like an HDFS path. Okay. Now the job has started. Another great thing here is that if you have an error when running your job, you can see it directly here. You don't have to go through the logs. As you might know, sometimes it's painful. Also, you can see the output of your jobs. And the thing that I talked earlier, you can go into the Spark UI Spark UI page and see the tasks that are running. So if you go to one of the stages here, you can see the summary metrics that I've shown you earlier. Also, if you don't like to use the UI, we provide a Spray client, an HTTP client that offers you a layer of abstraction on top of on the RESTful API. So you can
Would you achieve the same results if you run a Spark over Yarn and use Yarn to manage the Spark context?
Comparing to what?
Compared to what you have here with spawning of context and management and passing parameters and all that.
Okay, I'm just initializing the context and keeping it alive and offering you the support of running jobs on top of it. I'm not managing resources inside the cluster. So the Spark job REST is not like Yarn. So that's a resource manager, Yarn and Mesos, that
yeah, but it's capable of launching Spark as an application, right?
Yeah.
It seems like you would achieve the same thing and you would share the resources with other components too.
Yeah, I understand your question, but this is not a resource manager. You can set the amount of memory you want your application to have, but it's not a guarantee that it will receive it. We are using Spark job REST in order to manage context, but we're still using Mesos as a resource manager. Or yeah.
Can I help you? Very short. Imagine that he created a context, address the request to Spark. Spark is the one that is calling for a resource manager. And usually when you start Spark, you register methods of yarn and things like that, right? So it's up to Spark to do what it does. So what is the added value? It keeps the session in the resource manager. Either is yarn or methods. And it keeps alive all the RDDs in that session. So another job that uses the same context can receive information from another job. That's it. So it's up to Spark to configure.
I see. So you can link Spark contexts to each other.
So this you just keep a context.
What this project does, it allows you to spin more Spark context inside the same JVM, which is not possible. But you can run this context still on yarn or on Mesos. So Spark Job REST is compatible with yarn or Mesos as a resource manager. So they are separate things.
Okay, let my colleague Emma continue with the second part, creating data in-memory data warehouse.
Okay, so for building a data warehouse, I had, well,